Welcome back for the fourth lecture of this week. So in the last two lectures we had discussed a particular approach for dependency parsing, that was a transition based parsing method, and we had discussed how we can formulate parsing as a particular problem where we are starting with an initial configuration and moving from one configuration to another by using various transitions, and we modeled or learned these transitions using some training data that we already had. So this was a data driven approach. Now in this lecture we will talk about another data driven approach here. So the one main difference from the previous one is that we do not assume that projectivity constraint over the dependency graph. So in the last method that we had covered, we were assuming that the dependency graph that we want should be projective, although later on there are some variations proposed where this constraint is not required. So you might want to look into those. So coming to what we are going to discuss in today's lecture and the next lecture. So this is the approach using where we are formulating dependency parsing as a problem of finding maximum spanning tree. Now, what is the basic idea? So we are starting with a sentence that is given to me. So this is a sentence for which I want to find the dependency graph. And how do we formulate the problem? Firstly, think about this sentence as a set of nodes, these are the words, and assume that all the possible nodes are connected to each other. We will also include an additional node called root, so that we can find out what is the main head of this sentence. Now once we start by assuming all possible connections, my problem is to find out what is the maximum spanning tree from this all the connections that I can build, and this I would assume corresponds to my dependency graph, and the weights etc. that will be defined for this graph will be learnt by using some training data that is available to me. So the main idea here is I am given a dependency graph. So I start with a sentence, John saw Mary, and I assume an additional node like root, assume that initially everything is connected. So from root there are all possible connections to all the nodes, and each node has an incoming edge and outgoing edge with respect to every other node. How do we learn these edge weights? This is something that we will discuss, but assume that the weights are already given to you. Now your problem would be, how do I find out what is the maximum spanning tree from this graph? And this, suppose this is the maximum spanning tree, then this is what I will assume corresponds to my dependency graph. So my problem is starting from here to come up with the maximum spanning tree, that might be dependency graph. So now starting with some simple reminders from graph theory on what is a maximum spanning tree. So you are now familiar with what is a graph. So when I say graph, this is a set of V, that is set of vertices, and a set of arcs. Okay. So arcs generally connect two different nodes in the graph, and so arc is connecting to nodes I and j, both I and j are in the set V. Now if I talk about undirected graph, like the figure on the left, so if I say that I and j are in the set of arcs, then j and I are also there. There is no direction in this set of arcs. But if I say that my graph is directed, then if I and j are in the set of arcs, then j and I may not be in the set of arcs. Okay, like here I have a connection from this node to this node, but no connection from this node to this node. So now, so we saw what is a simple graph, undirected, and what is a directed graph. Directed graph can also be written as a digraph. Now we can also see what is a multi-diagraph. In multi-diagraph, what would happen between a set of vertices? There might be more than one possible arcs. Like here you are seeing between this node and this node, there are three different arcs. So that's why you will have an additional index saying I, j and k. Between the nodes I and j, what is the kth arc? Okay. So it's similar to the previous one, except that between two vertices you can have more than one arcs. Now once we know what is a multi-digraph, let me define the notion of what is a directed spanning tree of the MultiDiagraph. So once I start with the MultiDiagraph, that is set of nodes V and the edges A subgraph G prime, that is sum V prime A prime, is called a directed spanning tree if the following conditions are followed. What are the conditions? In the directed spanning tree, the set of nodes are the same as the set of nodes in the original graph. So I will have to take all the nodes from the original graph. Okay. So now what do I do with the edges? So the set of arcs that I take in G prime is a subset of the original set of arcs, with the constraint that the number of edges that I have now is equivalent to number of nodes minus 1. Okay. And the third condition is the graph G prime is a tree. There is no cycle in the graph. So let's take an example. So I have two different MultiDiagraphs that are given in the first and second figure, and you are being shown a directed spanning tree for these MultiDiagrams. So what do you see here? So it has the same number of nodes as were there in the original MultiDiagraph. And what about the number of connections? So you see there are 1, 2, 3, 4 and 5 connections, and number of nodes are 1, 2, 3, 4, 5, 6. So number of connections are exactly number of nodes minus 1. And you can take any possible set of any possible 5 connections in among these nodes, such that there is no cycle, and it will call it a directed spanning tree. Now once we know what is directed spanning tree, we can also define what is a weighted directed spanning tree. So here what we will do, in my graph with all the arcs I will also associate a weight. So each arc is now labeled or weighted by some numerical value, and this I will call it Wij. For the I between the vertices I and j, what is the weight for the kth arc? So Wij superscript k is the weight of the edge ijk. Now I will also define what is the weight of my directed spanning tree. So this will be simply summation over the weights of all the edges in my directed spanning tree. So from my MultiDiagraph I find a directed spanning tree. Definition was already covered in the previous slide. Now whatever edges I am obtaining, I will find out the weights for each of these and sum over that, and that will define the weight of my directed spanning tree. Now the idea here is, for a given, starting from a given MultiDiagraph, you can obtain a number of different directed spanning trees. So your problem is to find out which of these has the maximum weight. So now by this concept of weighted spanning tree, I have also defined what is the weight of a directed spanning tree. So now among all the possibilities, I will find out the one that is having the maximum weight. So starting from the graph G, let us say Tg is the set of all the possible spanning trees that I can obtain. So like this is an example. This MultiDiagraph is given, and there are these 4 possible spanning trees. So these are all directed spanning trees. Now I have to find out which of these has the maximum weight. So this is my MST problem, finding the spanning tree G prime of the graph G that has the maximum weight, and the weight is written simply as summation over the weights of all the edges of that graph. Okay. So I find out all the edges of that graph, sum over the weights, and that will give me the weight of the final graph. So now my problem is, from my sentence, whenever I construct a MultiDiagraph, that is all the possible connections, a fixed set of directed spanning trees are possible. Now among those, which is having the highest weight, and that is the one that I will say as my dependency graph. So now there are many questions like, how do I convert a sentence to an initial configuration, analogous to what we did in the previous method. Then the important problem here is, how do we define the weights of my edges, and once I define the weights, how do I choose the maximum spanning tree? So these are the 3 different problems, and then that's what we will be studying in this lecture and the next. So now for the sentence, how do I find the maximum spanning tree? So let us see, this is the first problem. How do I convert the sentence to the initial configuration from where I can start? So what is that? For each sentence x, you define the directed graph gx as vx ex, that is given by vx contains an additional node like root and all the words that occur in my sentence x. And what are my edges? I have all possible edges except for the same node. I do not have any self edge from the node to itself, but I have edges from every node to every other node, except that the root node will not have any incoming edges. That's why it is written here, the edges are from the node 0 to n to 1 to n. 0 denotes the root node. From root there are only outgoing edges, and for every other node there are both incoming edges and outgoing edges. So that is my gx is a graph where the sentence words and the dummy root symbol are the vertex edge. This is my set of vertex edge, and there is a directed edge between every pair of distinct words. Yes, that's what we have seen here, and a directed edge from the root symbol to every word from 0 to 1 to n. This is my initial graph. So now from a sentence I can construct this initial graph and assume that I have some method of finding out what are the weights of my edges. We will discuss this problem in the next lecture, how do I find the weights, but for now let us assume that we have some method of finding the weights of my edges. So I obtain a MultiDiagraph. Now my problem is, how do I find the MST of that MultiDiagraph? And for that we use a very famous algorithm called Chuli-Edmonds algorithm, and that's a very simple algorithm as well. So let us see what this algorithm does. So very simple steps. Each vertex in the graph greedily selects the incoming edge with the highest weight. Okay. So for each vertex in the graph, I have incoming edges from every other node. So what I will do in the first step, for each node I will select the incoming edge with the highest weight. So now I will now consider only those edges that have been selected. I will see whatever graph is resulting, is it a tree or not. If it is a tree, it has to be a maximum spanning tree, because each node has selected the maximum incoming edge. Now the problem is, if whatever I obtain is not a tree. If this is not a tree, that means there has to be a cycle. Now if there is a cycle, then there is a step that says you contract the vertices that are involved in the cycle in a single vertex. Now recalculate the incoming and outgoing edges for this new vertex that I have constructed. Rerun the algorithm, that is, again for each vertex choose the edge with the highest incoming edge. Again see if whatever you are finding is a tree or not. If it is a tree, you stop, otherwise you continue, and you can see that you will converge at some point. Why? Because at every step I am either finding a maximum spanning tree, so I am stopping, or I am finding a cycle. If I am finding a cycle, I will contract the vertices. Okay, so that means this will reduce the number of vertices that I have in my tree. So at some point I will have only one vertex, so that is the point I will have to stop anyway. So this will converge. So now again here are many questions like, how do I compute the weight for the incoming arcs and outgoing arcs? So let us see by an example. So I take the same sentence that we discussed in the previous method also, the simple sentence, John saw Mary, and I also know what is the dependency graph that I want to obtain. Now how do I start applying this algorithm? So as I said, the first thing would be, I start by taking all these three words as my nodes plus root as an additional node. So here you have root, John, saw and Mary as 4 different nodes. Next you make an edge between every 2 nodes in the graph. So from root you will have only outgoing edges. So from root you have an edge to saw, to John and to Mary, and for every other pair of words you have an incoming and outgoing edge. So from saw to Mary and Mary to saw, saw to John, John to saw, and so on. Okay, and there are some edge weights, and we are not bothering right now on how do we achieve these edge weights. So let us say I am given this sentence, I have some way of finding the edge weights, and I construct this initial multi-digraph. Now once I have this digraph, what is the next step of my algorithm? The next or the very first step says that each node in the graph chooses the edge with the maximum, so choose the incoming edge with the maximum weight. Simple. So there are only 3 nodes here that are having incoming edges. So let us see what is the edge that they will choose. So saw has incoming edge of weight 10, 20 and 0. So it will have to choose the edge with weight 20. Similarly, John has incoming edge of weight 9, 30 and 11. So it will choose the one with weight 30. And Mary has 30, 9 and 3. So it will choose 30. And then I will remove all the other edges. So I will have only 3 edges in my graph. Does that qualify for the maximum spanning tree or the diagonal spanning tree? It satisfies the first two conditions. Number of nodes will be same as the original graph, and number of edges will be 1 less than the number of original nodes in the graph. So I will now have 3 edges, 1 for each node as the incoming edge. So, but third condition is there should not be any cycle. So let us see, do we get a cycle or do we get a tree? So if I do that, I will get a graph like this, because Saw selected this edge, John selected this edge, and Mary selected this edge. So what are you seeing here? Is there a cycle? So yes, you find a cycle here from John to Saw and Saw to John. So that means, so I am not done yet. I have to now continue my algorithm. So what was the next step? Whenever I find a cycle, I contract that and make a single vertex. So the idea would be, so now I have a root node, then John, Saw, Mary. Okay. So what I have found till now, 20, 30, 30. Okay. This is not a tree, it's a cycle. So what is the step? I'll take it, I'll contract it into a single vertex. So there is a word J and S, let us call it WJS. Okay. This is a single vertex now. And I will have to repeat my algorithm. For repeating the algorithm, I should know to this vertex or to this new vertex WJS, what are the incoming and outgoing edges from all the nodes. So there are 2 nodes now. So root and Mary. So from root, it will have an incoming edge. From Mary, it will have an incoming edge as well as outgoing edge. So question is, how do I compute the incoming and outgoing weights from this vertex? And for that, we have some well-defined rules. How do I compute the outgoing edge weights, and how do I compute the incoming edge weight? Let us see how many I have to compute. I have to compute this weight 1. I have to compute. So now let's forget about this edge. I have to compute weight 2, and I have to compute weight 3. Yes, and root to Mary will be already there, that will not change. Yes, so I have now 1, 2, 3 edges, 3 vertices only, and I have to compute these edge weights. So how do I do that? So yes, so if there is not a tree, you have to identify the cycle and contract that, and you have to recalculate the arc weights into and out of the cycle. And what is the algorithm for doing that? So algorithm is that for outgoing arc weights, you take the arc weight that are equal to the max of outgoing arcs over all vertices in the cycle. What do I mean by this? So here is my contracted vertex, John and Saw. I want to compute the outgoing arc weight from this vertex to Mary. Yes. So, this will be equal to the max of outgoing arcs from John to Mary and Saw to Mary. Which of these gives me the maximum will be the final weight. So, here let us see from John to Mary and Saw to Mary. So, John to Mary I have a weight of 3 and Saw to Mary I have a weight of 30. So, among these the highest is 30. So, I will pick the one with 30 and this is the final graph that is being shown. So, from this vertex the outgoing edge to Mary will have a weight of 30 and that is the only outgoing edge for this contracted vertex. This is fine. Now, how do I find out the weight for the incoming arcs? So, incoming arcs are from root as well as from Mary. Yes. So, from incoming arc the algorithm is different. I do not choose the now. So, I have to find out from root to this vertex. So, I do not directly choose the one that is having the maximum. So, what I do? I have to also consider this the edges inside the tree. So, what I will do? I will take the incoming arc weights as equal to the weights of the best spanning tree that includes the head of the incoming arc and all the nodes in my cycle. So, what do I mean by that? So, let us take from root. From root there are two ways of defining incoming arc weights. Either it has to be root to Saw and Saw to Jaw or root to John, John to Saw. These are the two possible trees. Okay. So, what I will do? I will find out the weight for individual trees and take which one is having the maximum weight. So, let us say root to Saw, Saw to John. This is 10 plus 30, 40. Root to John, John to Saw. This is 9 plus 20, 29. So, I will take the weight as 40 and that is the edge weight from root to Saw. This is having a weight of 40. Now, can you compute the weight from Mary to this vertex? Again, I will see the two different ways, Mary to Saw, Saw to John. So, this is 0 plus 30. So, this is 30. Second is Mary to John, John to Saw, and that is 11 and 20, 31. So, I have two ways 30 and 31. So, I will choose one with 31. So, starting from Mary to John and John to Saw. So, now once I have computed all these weights, I have now got the new tree on which I have to compute my algorithm. So, here what did we find? This weight is equal to 40. This weight we found to 30 and this weight we found as 31 and this was 9. So, now once I have found these weights, what is the next step? I will have to see if each vertex now selects the incoming arc with the highest weight. Do we obtain a tree? So, let us see. For this vertex, incoming arcs are 40 and 31. So, it will choose this arc. For this vertex, 9 and 30. So, it will choose this arc. So, what is my what is the graph that I am seeing? So, let me color only the edges by this. So, one edge is here and the second edge is here. Yes. So, do you see it is a tree? It is a tree and this is a directed spanning tree. So, am I done? So, at one point I am done because there is no cycle. So, I do not have to repeat my algorithm, but I still have not obtained my dependency graph. Why? Because I am now stuck with an edge from root to this contracted vertex and I do not know what happens inside, and I know there is an outgoing edge from this contracted vertex to Mary. Again, I do not know what happens inside. So, how do I construct my full graph? And for that you have to go back to how you actually constructed these connections for this contracted vertex. So, what you will do? So, the incoming edge from root to John and Saw, and the outgoing edge from John Saw to Mary. So let us see, how did we compute the outgoing edge? We said the outgoing edge should be the maximum of both the outgoing edges. So from John to Mary and from Saw to Mary. And where did this come from? This came from Saw. So I will now say here there is a edge from Saw to Mary. Let me write it 30. Okay. So this is done. So this outgoing edge is from Saw, not from John. That's how we found it out. Now it's about the incoming edge. This incoming edge could have been from Saw then John, or John then Saw. In our algorithm, where did it come from? 40. So it came from root to Saw and Saw to John. Yes. So I have to now construct root to Saw, Saw to John. So root to Saw and Saw to John. Okay. This was 10 and this was 30, and that is my final MST, that is my dependency graph. Okay. So this is the algorithm. So let us see again here. So you are at this step where you have this contacted vertex and you found out the maximum incoming edge for each vertex and you obtain a tree. So now you have to go back up your recursive call and reconstruct the original graph, and there you have to find out where is this outgoing edge coming from. Is it coming from Saw or John? And you found it's coming from Saw. Incoming edge, is it coming for this tree, or that is root to Saw, Saw to John, or root to John, John to Saw? And that you can again find out. Where did you find this 40? It was from root to Saw, Saw to John. So yes, the edge from WJS to Mary was from Saw. So you construct that. The edge from root to WJS represents a tree from root to Saw, Saw to John, and that is your dependency graph. So now there might be a question in your mind that in my algorithm I have different ways of computing incoming arc weights and as well as outgoing arc weights. They are not the same. So we need them to be different so that we can also account for the weight for the connection inside the tree. But the question is, can I reverse this? That is, can I say that the outgoing weight should be the maximum of the directed spanning tree and the incoming weight should be the maximum among all the possible incoming weights? So I'd like you to think about it, but I can give you a basic intuition that why this is the case. So let us see. So suppose I have a contacted vertex that has nodes word 1 and word 2. So right now what we are doing, we are saying the outgoing weight is max of, so to a vertex like W3, it is a max of these two. Okay. Now so we take the max here. Suppose there is another vertex W4. I will do the same. The outgoing weight from here to W4 is the max of these two. Okay. Fine. Now when I have taken the max here and I am done with my call and everything, each vertex will choose only one incoming weight. So W3 will choose either this or this, W4 will choose either this or anything else. So that means I will know for sure whether there is a connection from W to W3 or W to W3 or there is no connection. And whatever I obtain, even if I say that from W1, suppose finally I find out a situation like this, that from W1 both the connections are there. This is valid. Because from a single node you can have two different outgoing edges. This is fine. Or if W1 and W2, that is also okay. In no case there will be two incoming edges for the same node. This is not allowed by the algorithm itself. Now suppose I change my algorithm and say that the outgoing edge is coming from the directed spanning tree. So that will be the situation where I will have to see. So this edge is the max of W1 to W2 to W3, and the other one, that is W2 to W1 to W3. Yes, similarly this will be the max of W2 to W1 to W4 and W1 to W2 to W4. Fine. Now what might happen, that in your final tree that you obtain, you find out this edge, yes, and this edge. Okay. Now you have to go back and construct your tree. So what you will see there, you will see that this edge is coming from by following this connection, and this is coming by following this connection. So you will end up by saying, okay, there is a cycle inside, and this will not terminate again. Okay. You can also try to see what will happen in the case of, so this is only for the outgoing edges. So you see there might be a case where you can end up finding a cycle, or may not be able to say which of these two is the correct sign between the edges. So this case might happen. This will never arise in the way we have defined the algorithm. Similarly, you can try for the incoming edges. Would you end up with a situation where you are either violating some principle of the dependency graph, or where you are getting a cycle and you are not able to converge? This is something I will say that you try to take both the cases and see whether you are finding why the algorithm proceeds in this way of for finding the incoming and outgoing edge weights. So fine. So we discussed this algorithm of Chuli-Edmonds and how do we use that for finding maximum spanning tree. So what we did not cover is how do we find the edge weights. Okay, and that's where the learning algorithm comes in, that how do we find out the edge weights for my dependency graph, and that's what we will see in the next lecture.